Okay. So to begin, I would like to do a few amendments to the previous lecture. In the previous lecture, we have discussed the relation between the standard deviation of a probability distribution and uncertainty. All right. And today I wanted to start actually to show you just a little Python exercise to give a little more feeling about how the standard deviation and the uncertainty of probability distribution are related. Okay, I share my screen, and please let me know if you are able. So are you able to see my screen now?
Yes, sir.
Oh, very good. Okay, so just a few words. So if you haven't seen yet Python, there are this couple of lines where we using some important packages, additional functionality that is provided by foreign developers for usage in Python. Then I define two variables, mean and standard deviation. SD is the standard deviation. Just for simplicity, I set the mean value of 0. So all the distributions that you will see will have standard deviation 1 and mean value 0. Then I define a function, is a function I call Gauss that takes an argument x and returns the probability density of the Gaussian distribution. So np.exp calls the exponentiation function to the base e. Inside we have x divided by standard deviation raised to the power 2 and with minus sign, okay, in front of the square. This symbol with double star, it's raising to the power 2, raising to the power, and 2 specifies which is the power base. And we divide by a normalizing factor. This factor can be obtained by integrating over all values of x. And makes the probability density to integrate to 1 square root of 2 pi square deviation raised to the power 2. Okay, uniform distribution. So you had an exercise, homework exercise to calculate its standard deviation and mean for a special case when x could take values only between 0 and 1. For that reason, the mean value of that distribution, which you considered, was 0.5. However, if we define if the values of x can take values from -1 to 1, we get a mean value of 0. But we can also make the distribution a bit wider. That expands its standard deviation. All right. So what I do here, I define the amplitude. What I call amplitude is just the absolute value of x, how large the absolute values of x can be. In your homework, the absolute value, maximum absolute value of x was 1. Here, I need to use the formula for standard deviation in order that the resulting probability distribution would have the standard deviation. Basically, I just need to expand the amplitude by square root 3 times the standard deviation. And this probability density gives zeros everywhere. So there is 0 probability to find x outside plus minus amplitude. And when our x is inside the region where x can take a value, it equals 0.5 divided by the amplitude. This definition of x points at which I interpolate the plot, which you see below. Okay, so we have a graph. Here you can see the Gaussian. It is a bell-shaped curve, blue line, and the uniform distribution. You see that probability density is 0 everywhere except this the little interval from almost minus 2 to 2. Okay, now question. So what will happen to these distributions if I increase the standard deviation by 10? I make standard deviation not equal 1, but by 10.
It will go wider.
It becomes wider, right? In terms of uncertainty, how certain we know the value of x in that case?
It becomes more uncertain.
It becomes more uncertain. Very good. Okay, what about the height? Okay. Wait. Let me ask someone else. Dionys, what becomes of the height of uniform distribution and Gaussian? In this region, uniform distribution, what will happen with its height if I increase standard deviation? Yes?
If we increase the standard deviation for the Gaussian, the height will, the height of the peak will be lower.
The height of the peak of a Gaussian will become lower. What about uniform distribution? What will become of it? Okay, thank you for the Gaussian. Let me ask someone. Anna, could you tell me what become of the uniform distribution if I make its standard deviation larger? So we have
the uniform distribution.
Yeah, so we have here a square. Yeah, it remains constant, so it will remain the same. So this square, what will happen with the square if I increased standard deviation by 10, which makes less certain our values of x?
If I increase the standard deviation,
yeah.
What is the question? What will happen to the?
What will happen to this to the shape of orange line, which is the probability density of a uniform distribution? Right now, this uniform distribution has standard deviation 1. What will happen if I make it 10? If it's uniform distribution of standard deviation 10.
It is not the same that it becomes wider.
Wider, very good. Okay, it becomes wider. What about its height?
Again, decreases.
Decreases. All right, very good. So I just now run it, and you see they flattened out. Now let me ask Said, what will become of these curves if I make standard deviation almost very large number, almost infinity?
It's I think becomes about 0. It becomes very large, and the height decreases at it becomes near 0.
Yes, true. So basically all this distribution will become just a thin layer above the axis x of infinitesimal layer. And actually they will coincide. So Gaussian, when you stretch it to make its standard deviation infinite, becomes also uniform distribution. And it's actually a feature of all distribution, whatever you take. As soon as you stretch its standard deviation to become infinite, when, in other words, your uncertainty is infinite, you know absolutely nothing about possible values of x, for each value has the same distribution, all distributions becomes uniform from minus infinity to plus infinity with like infinitesimal layer of density, which if you integrate becomes 1. Okay, Boris, what if I make my standard deviation now 100 times less? I make it 0.1, 0.1.
The amplitude will be increased.
Yes, amplitudes will increase. You see, it's not even fitting anymore in the graph, so I have to make the y-axis a bit longer. Let's make it 5. You see, what happens, they become, they start to peak up and become very, very similar. Because what will happen when I decrease standard deviation to 0? Boris.
There should be a vertical line in 0.
What?
A vertical line in 0.
Vertical line in 0, which is, how do you call such a distribution, a vertical line in 0?
I don't know.
Who knows? Haya, do you know?
Delta function.
Delta function. Yes, sorry, Haya, someone, Idris was eager to answer. Okay, it becomes delta function. That's because all distributions, when it doesn't matter if it was Gaussian or uniform or triangular, if you make it standard deviation 0, they all tend to be one distribution. In the limit of 0 variance, they all tend to be delta function. All right? That's why, in principle, it's often not that important. Yeah, it's an important detail about a variable, let's say a position of a particle. If you are very interested in that particle, it's important information what exact probability distribution it has. But in principle, it's sometimes just enough to know how large is its standard deviation. In other words, standard deviation is a good statistics, a good measure of uncertainty. Is it clear, or anyone has questions? Does anyone have questions?
Sir, can I ask?
Yes.
For this, from what uniform distribution should have equal or constant distribution for all the points. But for this graph, the standard deviation of the function defines the range. Is it like that? Or the range of the interval?
The range of interval. Well, yeah. Sorry, can you maybe clarify a little?
For that, the x points was from -5 to 5.
Yes.
So, but the uniform distribution depends on the standard deviation. So the range of points is also changing?
Yes, range is also changing. Yes, indeed, because if you say that I have uniform distribution from -5 and 5, so to specify a uniform distribution, you just need to give a constant, okay? Constant. You remember we called this constant C in the last lecture, and then we found the value of this constant by integrating over the values of X that were admissible. So there is only one thing that we can change in this distribution. And then if you want to make it standard deviation, so if you fix C, its standard deviation is fixed. The only way you can change the standard deviation is to change C. But to change C, you also need to change the normalization condition. And that's where you need to change the limits of integration. And then if from -5 to 5, the probability was 1/10, then to make standard deviation larger, you would need to expand, let's say, from -10 to 10. Your uncertainty, of course, became larger because before you were sure that -7, value -7, for instance, was not possible for the variable X. But when you increase the standard deviation, yes, -7 is a possible value. Does it answer your question?
Okay. Okay. Thank you, sir.
All right, other questions? Okay, if there are no other questions, let's then continue.
Excuse me.
Yes.
I had some problem with working with this Jupyter notebook. I couldn't access the file. In fact, I have the files in the Google Drive, but I can't just open it using the Jupyter.
Wait, okay, so I did not send any Jupyter notebooks to you. I believe that this is something that you were talking about, something you were talking about with Andrea Mazzolini. Is it
I think so. Yeah, yeah.
Right. So you better ask him and ask his assistants to deal with your problem, because I don't know. I can't even look up what notebook you are talking about right now. Okay.
Okay.
Okay. I'm sorry I couldn't help, but anyway, you may resolve this issue with Andrea. All right. Other questions? No questions. All right. Then let's begin the new part. All right, today I wanted to start a discussion of thermodynamics, since we discussed last time that statistical physics, statistical mechanics was developed, first of all, to explain how thermodynamics works when we accept that the matter consists of atoms and molecules. And that's why we will have a little review the thermodynamics. So first of all, let's talk about thermodynamics. And one thing that usually we must first define in the thermodynamics is the concept of equilibrium. For instance, Said, could you tell me how would you define equilibrium? Thermodynamic equilibrium.
In thermodynamics, when a system is in equilibrium, when no energy enters to the system and no energy exits from the system, and there is no interaction in the temperature, in pressure, or there is not a volume change.
All right. Thank you. Haya, would you have, would you agree with Said, or would you have other?
So basically, if the macroscopic state of the system is not changing, then we're in thermodynamic equilibrium. So
All right.
the properties like volume and all, the macroscopic things, if they don't change.
Yes, that's right. Yes. So basically, Said was talking about interactions, but I believe that what he actually meant probably was what Haya phrased better. There is no change of energy or temperature. Not that there is no interaction. For instance, if I take a cup and put here water, there will be still. Sorry, do you see me or only the screen?
Only the whiteboard.
Only whiteboard.
Both actually, it depends.
Okay, yes.
You can see also my face.
Yeah, I see it,
okay.
Both the screen and you.
Well, okay, probably screen is better. Anyway, if I take the cup and fill it with water, in the days when thermodynamics was developed, we did not know. We do know people, researchers, they did not know, or were not even sure that matter consisted of molecules. So thermodynamics was a phenomenological thing, and then if I put water in a glass, it interacts with air, with surrounding. So interactions there are. But what people observed that I could define macroscopic variables like temperature. We could invent, and we did, people did invent thermometer, that we could measure temperature of water in this cup, for instance. And then what was observed that after some time, if I don't leave the system to be, like leave this glass of water to itself, the temperature of the system with time obtains some value, which later does not change. All right, so there are no changes of some variables. Okay. Then we could do experiments. I could, for instance, take a spoon and mix, take a spoon and start to mix water. And then I would observe that water rotates, okay? Then if you have heard of this concept of, I'm sure you have heard angular momentum, the water would have some angular momentum, right? It would rotate. But then if I leave it for some time, I will notice that water again becomes just as if I did not do anything. So it completely forgot that I was doing something with a spoon, that it had some momentum. It again came to the same state that was before. And I could, for instance, take a heater and start to to put this cup on a stove and start to warm it up. And then as soon as I take my cup again from the stove and put where it was, after some time, it comes exactly to the same state. And that when I again put thermometer, it shows me again the same temperature. Then the researchers who were working on this problem, they came to conclusion that there exists a state which we call equilibrium. And we define just a postulate that such state exists, and all systems, if you leave it to themselves, you don't do anything with these systems, they come to this state of equilibrium. And in this state of equilibrium, we can define some macroscopic variables like temperature, total angular momentum, and these values will not change at equilibrium. It's important, however, I think, yeah, the concept of equilibrium figure in classical courses or in many contexts of chemistry, physics appears very often, so that at certain point, students often start to think that everything is equilibrium and start to apply without thinking, apply theories designed for equilibrium systems, start to apply these theories everywhere. And not only students, actually, even in some decades ago, some renowned physicists, active scientists did similar mistakes. So there is not much of a big, it's a big mistake, but nothing to be ashamed of. Tell me, what systems so let's define something which is not a non-equilibrium, so that you could fancy systems which are not equilibrium systems. Kyrell, could you tell me, give me example of a system that is not in equilibrium?
The simplest that I can say is what I'm looking at outside, which is the waves in the sea.
Waves in the sea.
I mean the water.
The water. Waves in the sea, water in the sea. But you know, actually, yeah. If I measure temperature, the problem is here that if I put temperature, probably today it will give me a temperature of the sea, and after 10 minutes and after 2 hours, it will be the same. I will tell, maybe we'll return later in the course to this problem. The problem is that you take a very large object. So for instance, if you were like Gulliver, a few kilometers in height, these waves for you were like, you know, a lake, water in the lake. You just approach and you see no waves there, just smooth, surface of water. And all right, who can give another? Who has thought of another system in non-equilibrium?
Your cup of tea in your table.
Cup of tea. What do you mean?
It's
Ice tea.
It's a small system that it might be very hot now, but after 10 minutes, when you see its temperature has decreased.
Okay. Yes. Yes. And in fact, the truth of life is that in nature, whatever we see around, nothing is equilibrium. Everything is non-equilibrium, but in many situations, things are very close to equilibrium. Or in a subjective way, if I put temperature, I could see if temperature changes or not, right? Or define some observables that would tell me that if I see that these observables like temperature, angular momentum stop changing, then it's equilibrium. In that sense, for instance, example with C is also correct that it's, yeah, you see, obviously it's moving, something is changing with time, but temperature does not. And so for me, I could say that C is an equilibrium. And actually, if we again recall that everything consists of molecules, so if I put water and leave it to equilibrate, when it reaches equilibrium, there are molecules, and molecules, they all the time moves, just like waves in the sea. They happen. It doesn't yet mean that I cannot describe the system as equilibrium. Because again, the matter is macroscopic observables that describe the system as a whole. So waves is like motion of molecules. Okay, it is motion of molecules, but temperature is a macroscopic observable and stops changing, then it's equilibrium.
I have a question.
Yes.
Are we talking about equilibrium in a general way or thermal equilibrium?
Thermodynamic equilibrium, yes, thermodynamic equilibrium. But can you tell me what?
It's not just related with temperature?
In what sense?
Or it can be with another macroscopic variables, because the zero law does not talk about the two systems reach equilibrium when they reach the same temperature.
Yes, the zeroth law, exactly. So temperature is actually the first thing that you want to check. Yes, thermodynamics first, the zeroth law is actually talking about temperature, but sometimes your temperature, let me give you just a thing that is very similar to equilibrium, but it's really non-equilibrium. So I take, for instance, this spoon and I put ice on one end. I just, one end of the spoon, better this end, I put inside ice, okay, here ice, and here I start to warm it up, okay? After some time, what will happen is that if I put thermometer over here, I will measure temperature at this point, but it won't change with time, just as long as I apply refrigeration, the ice which makes the spoon, one end of the spoon cold, and on the other hand, on the other end of the spoon, I apply some heating, I heat. That would be a non-equilibrium system. And a good thing to note, so macroscopically, almost nothing changes. There is just one thing. There is a flow of heat. So there is, it's always that I have to put heat. As soon as I remove, for instance, heating, temperature will become the same in whole the spoon, as predicted by zeroth law of thermodynamics. It will be the same temperature as the ice. But the important point is that there is a current. It's called steady state. Steady means nothing changes time, but there is a current of energy. There is energy that I put in one end, it flows through the system to the other end, okay? other examples of non-equilibrium, I can heat a little bit, but then I heat the other end of the spoon and make cold the other, and do it in time, change it in time. In principle, the situations of systems in non-equilibrium, there are examples of non-equilibrium systems are much more. It's a larger class of systems. And equilibrium is only a particular state. When you really stop doing anything, you stop putting energy inside the system with heating, or remove energy with a refrigerator, something like that. Then your system is in equilibrium. And another, well, very simple class of systems that often considered is other systems, irreversible processes, or let's say systems in transient state. Let's do this. I have, for instance, imagine a box of gas. So I put here a wall, and here there is a gas, okay? And it's an isolated system. Here on the right, there is nothing, a vacuum, for instance. And there is a wall that separates one compartment of the box from the vacuum, another compartment with the gas. Then if this gas is isolated system, it comes to an equilibrium, okay, as postulated, there is these states, we wait sufficiently long. But then, so for instance, we even put thermometer and measure a temperature T, okay? And then I removed this wall. As soon as I remove this wall, what will be the temperature of this system? Who can answer?
It will be T after a while. It will take some time for the gas to redistribute itself.
Okay, so here the thing. So how would I know that it's a temperature T?
You measure it
You measure it. How do I measure it?
with a thermometer, like you did.
Thermometer, right? What is essentially thermometer? Thermometer is a system, okay, like mercury, for instance, thermometer with mercury. So it's a system which I place in contact with my system. So I put here another second system, which I call thermometer. Okay, and I wait till it's okay. This is thermometer, and I wait when it's equilibrated with the gas. Okay. But while I wait to equilibrate, which means that I wait that nothing will change, the gas already occupied all the volume, right? It already reached a new state of equilibrium. And so whatever I can measure will be the temperature of gas when it's already occupying the whole volume. So in this moment, when I remove the wall, the thermodynamic, the classical definition of temperature, cannot be applied. The temperature, thermodynamic, classical, in the classical sense of thermodynamics, does not exist. You can only define temperature for an equilibrium system. Is it clear? Who has questions about this statement? Hiya, are you convinced?
I was having difficulty with my headphones, so I didn't hear a bit of it, but...
Okay, so what I'm telling is that, okay, so...
I mean, I heard the part about introducing the thermometer, which will change things, but that would change things for this piece of, as in this side of the wall as well, when you measured the temperature, right? At that point, it would change as well. So it's the same thing as that when we remove the wall.
Yeah, so the point is that, okay, when the wall is there, nothing changes, okay? And then
No, but when you measure the temperature of the gas with the wall, then the same
okay.
thing happens. No?
With the wall, well, the point is here that thermometer is a very small system, so that we consider, it is true in general. The point here with thermometer is that thermometer is very small, and therefore it does a little bit change in the system energy, but does so very little that we think that we pretend that this interaction was negligible. The only point, here is that at macroscopic scales, as we say, so we should observe that nothing changes in time. And when we remove the wall, of course, things will start to change in time. And while they change in time, while things change in time, temperature as a thermodynamic macroscopic variable in classical sense of thermodynamics is not defined. This is called, you can say it's a transient state. So it's a system in non-equilibrium, which relaxes towards equilibrium. And as you know, when gas will occupy already whole the volume of the system, that's when we finally reach an equilibrium. Then we can detect with thermometer that nothing is changing in time. Questions? All right, so if there is no question about that, but just for future, if you detect in a system that there is a current of anything, of heat, of particles, that's for sure a non-equilibrium system, okay? Even if you, for instance, can see that temperature does not change in time, it does not always mean that system is in equilibrium. But if your system isolated in the sense that you don't put anything inside, you don't mess up with the system, then if you detect that nothing or temperature, for instance, does not changes, then it's a thermal equilibrium. Okay, zeroth law of thermodynamics. Someone wanted to tell me this higher. You were trying to tell the zeroth law of thermodynamics. So could you tell us?
I think it was Anna.
Anna, you wanted to tell us the...
That's not fair, Haya.
No, but you mentioned it.
Okay, I could mistake. Yeah, I'm not always observant who was saying something. Okay, Anna?
I don't remember the state of the...
Okay, in your words, zeroth law of thermodynamics.
Then when you have two physical systems interacting, they will reach thermal equilibrium when they reach the same temperature.
Yeah, almost. Yeah, usually, actually, this zeroth law, okay, it's called zeroth for a reason that
it was discovered later.
Later than first, right? And then they wanted to put it a little earlier in the hierarchy of laws to emphasize its importance. Well, usually it is, for instance, in the notes that we suggested for reading, it is defined with three systems. That it's just actually to emphasize that the equilibrium is a transitive property, as in sophisticated words. What it says is that if you have three systems in contact, so if you have a large system and you know its temperature and you put the other two in contact, and then the other two will equilibrate, and they will have the same temperature as this first system. All three will have the same temperature. But the main point is that there is temperature, the property temperature, which is, let's say, it can be a number, a quantity, physical quantity, which is equal. So a temperature of one system is equal to temperature of the other system. When this happens, you are in an equilibrium, okay? So when you, sorry, when the other way around, when you know that two parts of systems are in equilibrium and the whole system consisting of these two systems is in equilibrium, there is temperature. And the temperature, if you measure it in one subsystem, will be equal to the temperature in the other subsystem. All right. Okay, then internal energy. Okay, another concept which we'll need to formulate the first law of thermodynamics. What is internal energy? For instance, yeah, last time we started already discussing particles. A convenient of an object to statistical physics is a box of molecules, which we call ideal gas. Why ideal is that these particles, they do not interact with each other, so they can move around. But if they sort of go one through the other without noticing, so they do not repel each other or something, even like if you were thinking of hard balls, which elastically collide, this is not the case. They literally, like two ghosts, go through the other. And the only thing that provides some potential energy is the wall. So the wall may repel the particles when they approach, when the particles approach the wall. Then in classical mechanics, we can define the Hamiltonian. So it would be P squared 2m, sum over all I, and particles, right? Yeah, let's assume that all particles have the same mass, just doesn't change in principle much. And as well, there is a potential energy, but let me call the coordinates of particles Q. You see, its potential energy depends only on the position of the particles. In other words, if it's close to a wall, it may feel some repulsion when it's inside, maybe repulsion is less, but it doesn't care where the other particles stay at this moment, okay? Then what would we call internal energy? For instance, Idris.
It is the difference between the total energy of system and the heat.
The heat, so heat, and what is heat?
So heat. Okay, so I can say intuitively, heat is just how fast particles are moving.
It's basically this Hamiltonian, no, because it's a sum of
yes, exactly.
energy.
It's energy. It's energy of the system. And by the way, you probably often heard that. So, for instance, I could add here a number, I don't know, 150 joules. It has absolutely no effect on the dynamics of the particles. Okay, just to say. So. Right now we'll discuss why it's important, but in principle, it's the Hamiltonian. Yeah, usually it is the Hamiltonian. Now, yeah, so basically this E, for instance, these Stanford notes, they even suggest to use E instead of the letter U appearing in many texts. But yeah, so we say that Hamiltonian of the system gives us energy, E. Okay. And then, okay, internal energy, I could define this Hamiltonian as this Hamiltonian, but then what happens if I start to move? So I add some velocity to the walls and to all the particles simultaneously. Will the internal energy change?
No.
Idris, can you? No. So could you explain why?
No. Okay. So from theoretical background, because in the Hamiltonian expression, I mean the internal energy expression, there is no information about the position of the box or its velocity.
Well, yeah, in principle, yeah, there is no information, but the point is that we, okay, if we work in the Newtonian picture, inertial frames, you know, should be equivalent in their mechanics does not change. So if the whole thing moves with some constant velocity, Newtonian equations do not change, okay? The system, then we would not expect that anything, since we believe that thermodynamics is emerges out of this microscopic laws governing the motion of molecules, then we have to accept that also thermodynamic properties would not change.
Isn't it like if we're adding velocity, isn't it that we're adding kinetic energy? And if we add energy to a system,
Very good.
there is conservation of energy, as in
Yes.
energy cannot be created, neither created nor destroyed.
Well, yeah, let's take this argument. Yeah, so it is interesting. So let's expand. So basically, we can say that, okay, in this simple case, for instance, the kinetic, what is the momentum of a particle, right? It's a mass times
Velocity.
times velocity, right? M V, let me call it V. Oh, Q dot. Okay, dot stands for time derivative squared over 2. Okay, plus V. Let me denote this V of I. Okay, just not to write the QI. Okay, now we added basically everywhere their constant velocity, right? Then how this would change? Okay, that would give me m of qi plus, let me put a bar, plus v. I added to all particles some constant velocity. This is squared over 2 plus the capital V, the potential. And here it depends on the distance. Okay, let's assume that it depends on the distance from the wall, right? But then if the wall moves with the same speed as all these particles, then it does not matter, right? So the dynamics will be exactly the same. Then let's have a look at this term, okay? Qi plus V. Who knows what is center of mass?
In classical mechanics.
Yeah, how do you define the center of mass?
I think it's the product of the mass by the distance between the center to the point we want to compute the center of mass. According to Huygens.
Yeah.
It's average position of all the internal particles.
Yeah, yeah. So it's average position with respect to mass. So how we define the center of mass? So the center of mass is the sum of positions divided by total mass, okay? Which is the sum of all particles. It is just n over n times mass of each particle, then times and sum over all their coordinates, okay? Yes?
There's a mass missing, multiply.
Yes, true. Yes, here is mass, which then cancels, and then yeah, then it's average position. Okay, in this simple case. But then what is so we call it capital R. Okay, so what is the velocity with which the center of mass moves? It is just the sum of velocities, right? We just put a dot, time the differentiation, n does not depend on time. We differentiate with respect to time the q, the positions. Okay, then there is a such thing as positions. We can define our positions as new positions as position minus position of the center of mass. Okay, and then the velocity prime q dot prime equals q dot minus r dot. Okay, now I need a new page. Okay, maybe no, I can expand still. Do you see the screen? Is it visible what I'm writing?
Yes.
Okay. Okay. Now look, the point here is that the sum, since we already subtracted the center of mass, the sum of qi prime, what it is equal to? Who knows what is the sum of qi primes? Boris.
And R1.
So
is R1
R
factor 1 dot R dot factor n factor n minus 1.
Factor n minus 1 y. No, actually, so actually it is the 0, you see. So okay, R. So R was equal is the sum of all coordinates, right? Then, if we already subtracted from the coordinate of the center of mass from all coordinates, and try to compute what is the velocity of the this primes is actually the center of mass for the new coordinates. But since we already subtracted the coordinate of the the coordinate of the center of mass, then also the velocity we subtracted, right? So nothing, the sum of all velocities with respect to center of mass is 0. The new center of mass is at 0. We shifted everything, the origin to the center of mass.
Yeah, and instead put 1, this n r dot.
Yeah, this must be 0, okay? And so we could define, so if we substitute here, actually the new velocity, qi dot prime, sorry. Qi prime plus r dot dot. So if we substitute instead of old QIs, we see that what's inside these brackets is merely QI dot plus prime plus R dot plus V. Okay. and this is squared. In other words, what we did by moving the whole system is only to start move the center of mass with the velocity v bar. Okay? Is it clear? Who has questions? Okay, so let's call this r dot prime, and then, okay, let me erase here. That was premature.
Excuse me, could
yes?
you please describe what we are going to do here?
Yes, so now I start to open up this
from
sum.
beginning when we
yes, okay,
Hamiltonian.
Yes.
After that, what we are going to do?
So I'm trying to show you that in fact what we did by adding the velocity, okay, the final point where I will arrive is actually that it's the same as adding when I added velocity v bar to all the particles and the walls of the container. What I added is just a constant to the Hamiltonian, okay? Ultimately, if I open this bracket with the substitution of r dot prime instead of dot r and v bar and q dot prime for the velocities with respect to the center of mass, I will pick up this squared over 2 plus q bar dot r prime dot plus r prime dot squared over 2 plus v of qi, okay? And then if I apply this sum to this term, this is a constant, I can take it out of the sum, so this term will cancel. This term remains constant, okay? And then what I got is a Hamiltonian with a new set of coordinates q prime instead of old set of coordinates. Plus some constant. And this constant is just some one, so r dot squared over 2 times 1, okay, and sum over I, which is
I'm
just
kind of lost. What are we doing?
lost. Okay, let's repeat.
Not with the calculations.
With what?
With what we're trying to establish or understand.
Okay, we are trying to establish that. So, okay, does everyone understand that this calculation leads to the fact that adding constant velocity to all particles and to the walls of the container, it only leads to adding a constant to the Hamiltonian?
But that's what we did with 150 joules.
Yes, it's an example. I don't know if it will be 150 joules, but what happened if we added 50 joules, right? So the whole point is here is that in principle, what you care is only about the motion, the Hamiltonian with respect to center of mass, okay? So if the whole system is moving with the same velocity, so the velocity, what means, in other words, if the system moves with the same velocity, that means that center of mass moves with the same velocity. What I have shown, this change of system leads to adding a constant term to Hamiltonian, okay? And the change, adding a constant to Hamiltonian changes absolutely nothing in the dynamics of the system, okay? Therefore, what I'm trying to say is that as internal energy is usually we take merely the energy with respect to center of mass. Okay, is it better if I phrase it this way? Does it make it clear? Aya?
What happens to the center of mass?
The center of mass, yeah, does not matter what happens to the center of mass. This is the point. If the center of mass of the system moves with some constant velocity or it remains fixed at one place, nothing happens to internal energy. Do you see why?
It's the first law of thermodynamics.
Well, the first law of thermodynamics actually does not define what is internal energy. So it is in this picture when we start to consider a gas of ideal gas or some concrete system, that energy takes a specific microscopic form. So we have a microscopic definition of energy. Hamiltonian uses coordinates of all n particles to give you the value of energy. And the main point is that adding to this Hamiltonian any constant does not change
No,
the
but
thermal energy.
Doesn't the first law of thermodynamics talk about the change of change in a system's energy?
Which change in the system's energy? Yes, but it talks about internal energy, okay?
So what were we talking about?
We are talking about how internal energy manifests itself in the form of Hamiltonian. So what I am telling
So
is
it's the same thing, no? It's still the internal energy.
Well, if I add to Hamiltonian 150 joule, Hamiltonian, the value of Hamiltonian changes, right? It will be energy plus 150 joules, right? But to find the internal energy of this system, I need to subtract actually the center of mass, right? And then in the center of mass, I will always have the same value of internal energy, right? If the center of mass moves with velocity 100 kilometers per hour or 2 kilometers per hour, the value of Hamiltonian will change, okay? But the value of internal energy, if it's calculated with respect to coordinates defined with respect to center of mass, internal energy does not change, okay?
Okay.
So there is a way to define microscopically for a system like ideal gas or classical mechanical system, an internal energy, okay?
Okay, thank you.
All right. Now let's go to the. So let's review a bit. Recall the Hamiltonian dynamics in case you don't remember precisely the rules. How the Hamiltonian. Who remembers the Hamilton equations? How the QI and PI change? Dot QI, which is d over dt. T is time of QI, and this is d over dt of pi. Kyrell, if I give you Hamiltonian H, right? This is H of QI and pi. How can I find from Hamiltonian the velocity of the particle QI? Kyrell? Do you know how to use Hamiltonian? All right. Who knows? Dionys, do you know?
From the Hamiltonian, we get the velocity.
Yeah. How to find velocity of particle QI if I give you Hamiltonian?
Not sure. So
Do you know what? Huh? Yeah. What do you know what is Hamiltonian equation of motion?
Is it the pi squared over 2m plus v?
No, I even give you. This is the
Isn't
Hamiltonian.
it the are we talking about the generalized equation over here? Minus partial h over partial q and
yes. That's all right.
plus partial h over partial
So
q.
it's not minus. So this is, so you take the Hamiltonian and take its derivative with respect to
Time.
to qi. No?
Yeah, to qi.
Okay.
Because over here it's time. Yeah.
So what it is? So these terms. Oh, sorry, to pi. That's yeah.
Yeah, that.
Yeah.
Hence the minus sign.
No, minus sign. That's funny. Yeah, actually, in one equation there is minus, but not this one. So
actually, I'm confused because you overwrote this one. I thought it was p.
so dqi pi. This is the form, right? V does V, capital V, for the potential energy does not depend on P, right? So its partial derivative with respect to P is what? Idris?
Constant.
So, okay, if we know that V depends only on Qi.
Oh, 0.
0.
Okay, this is going to be the zeros. Then I take the kinetic energy term, okay? Sum of I, pi squared over 2m. And then I want to differentiate it with respect to pi. What do I get?
2 pi over 2. Pi over m?
Pi over m.
Summation.
Summation. Why summation? Yeah, okay. I can change this to J. Then, I mean, okay, let's consider a concrete example. So I take the second particle, momentum of second particle, and there is a sum, right? There is a sum. And there are 3 particles, n equals 3, and it's 1 dimension, just p1 squared over 2m plus p2 squared over 2m plus p3 squared over 2m. Okay, if I apply differentiation to this term, what do I get?
P2 over m.
P1 squared over 2m with respect, differentiated with respect to P2 is
0.
0. P2?
P2 over m.
P2 over m. P3?
0.
Yeah, you see, so sum disappears. There is only one particle, pi, okay?
We can use the chronicle delta to define it.
Yeah, you can. All right, but then what with the second equation? How the momenta change?
With respect to qi this time.
So Dionys, you want to answer? So I partial differentiate qi
of Hamiltonian with respect to qi. So
qi.
only the v
that's all
of qi maybe.
Okay, so I take so there is something missing in that equation. Let's figure out what. So okay, if I differentiate now, if I now differentiate this sum or the kinetic term, okay, this term with respect to qi, what will I get?
There's
nothing.
Nothing. It's 0, right? So kinetic term does not give me and VQI. So I have now I have now a sum over I, V, Q, I. Kinetic term gave me 0, so I need just to differentiate this with, let me call it J. Okay, here J, and this is Qi. What will I get?
Partial of V with respect to Qi.
Yes. So what do we miss in this formula? So there is a partial V, so potential energy. Okay, so imagine an abstract example. This is potential energy. This is position. Okay, V. This is Q. Okay, if I differentiate this potential with respect to Q, so the derivative is growing, right? And then does it mean that particle accelerate to the right?
Minus sign.
Yeah, minus sign, because potential acts in the opposite side. So particles try to acquire velocity as such that they move away from peak of the potential. So the direction in which potential grows is exactly the opposite to which the particle tends to move. That's basically expressed by minus sign here. So you see, so it's almost beautiful in a way that this structure is called symplectic sometimes, if you have heard this word. So it's dH over dPi, and it would be so nice if it was dH over dQi in the second equation, but you must put minus sign. All right. Okay. And so, just again, we're recalling these simple things. Okay, I'm raising. Okay, let me. How to erase very quickly. Okay. So this is it. Okay. Now about isolated systems. So this system is isolated. So, and we already know that H is the energy, right? Then how now this, so I want to find the dot is a time derivative of energy, how energy changes in time. So I differentiate the Hamiltonian with respect to time. Okay. Sum over I, when I squared over 2m plus v over q I. Okay, so I put it inside the sum. What do I get from the kinetic term?
So 2 pi dot
2 pi
pi dot over n.
2 pi
Dot
divided by 2 over m, yes, which can be simplified, right?
Yeah,
P dot E, exactly,
Yeah.
chain rule. What do I get here, Boris?
Qi dot
Qi dot
derivative of v inside, yeah, d prime qi.
Mm-hmm.
Yeah.
All right. Now, what is, I put prime, but okay, let's not put prime. It's not very nice. Okay, so derivative of qi. But what is derivative of v with respect to qi? Boris.
V dot.
So derivative of v with respect to qi.
Is v dot. No, v prime, not dot. V prime.
Well, v prime, I'm sorry, I was going to use this notation. I don't use prime. You tell me just a different notation of derivative.
The force.
The force, okay. What is the force? Have you seen this equation here?
Yes.
So
M.
So dv pi, just pi.
The derivative of pi.
Minus pi, exactly, okay. And pi over m is what?
Qi dot, yes, Qi dot.
Q dot pi dot. And here, second term, what is second term?
Plus Qi
plus Qi
dot.
pi dot.
Pi dot. I think you have minus.
Yeah, exactly. That's what that's what is important. That here we have the minus sign because this a little strange minus sign, but it's here. And then what do we get?
Summation of pi.
Yeah, summation of dot qi dot pi minus dot qi, 0. So we just have shown that the energy of this system does not change in time. Very famous consequence. So I used this fact actually yesterday, but if you haven't seen, it can be proven just like that. Okay. So when we tell that the system is not disturbed from outside, when I say that it's an isolated system, what I mean is actually that the derivative of Hamiltonian is going to be 0. Okay, how we can imagine a system just formalize? How could we create a system that that depends on that is disturbed, right? Okay. For instance, I could add. So this will be Hamiltonian 1. Okay. So it's almost like my previous example, but I add here another, for instance, term, which I acceleration times, for instance, qi. Okay. So like a gravity. Okay. So things tend to fall on the floor of the container. Okay. But it's funny gravity that I have some device that can manipulate with time. Okay. So I can adjust at my wish this constant g. So it's a function of t. Okay. Now I want Idris to calculate for me this. What is it? Partial dh. So we can say that now dh is a function of qi, pi, and explicitly of t. What is the partial derivative of h with respect to time? Idris, can you calculate that?
Can you repeat the question, sir? I just disconnected.
I want to take partial derivative of Hamiltonian H1
Yes.
with respect to time.
Yeah. So we did the same calculate already. So we just make the derivative for GT multiplied by Q.
Yes, what should I write? Okay, sum of I. This thing.
No, for the first two terms we already did the calculation, and we found it zero.
No, but
It's zero, no?
it's a partial derivative, so it'll just be G dot T into QI.
Yes, exactly. So, so PI is we consider as a being variable. That's what indicated as a derivative. In itself, it's dependent on time, but in this notation, I emphasize that we consider it as a variable of this Hamiltonian. Okay, so partial in this notation, partial derivative of PI with respect to time is 0. Also, same goes for the partial derivative of V with respect to time, because it's a function of Q, not of T. The only thing that can be differentiated with time, with respect to time, is this term explicitly, okay? For this part, we have just made a calculation. It would be exactly the same. This term, when we differentiated them with respect to time, would give us 0. And then we would obtain only this term dt, d over dt, g of t times qi, okay? So this not to be confused, for instance, with the notation when you have d over dt of h. When I write d, not partial derivative like here, but with the Latin letter d over dt, that means that I need to go inside pi and consider pi as a function of time. And so I do with respect to qi. But if I write partial derivative, I don't do that. Okay, so it is, so what I want to explain is that this symbol with the Latin letters d, not the symbol of partial derivative, it means that I need to differentiate Hamiltonian with respect to each function, to use a composition rule.
Yeah.
And to take then derivative of each function of time. Okay. Yeah, so we had, sorry, Hamiltonian one with the, okay, qi. Yeah, sorry, yeah. I already did a bit, we just use not explicit zone. And then dh1 over dt. And d over dt. Yeah, I'm sorry, sometimes it is actually abbreviated. I'm trying, so sometimes instead of writing this, people just write this, okay? T is a subscript. So I'm sorry if I sometimes do not use the full notation. It comes automatically to me. Okay, then this part we already calculated, right? And it was 0. But this part we have also just calculated. And so what we have, oh, by the way, the bracket should have come here. And then what we have that now, in this case of Hamiltonian H1, in case of Hamiltonian H1, the energy was dependent on time, okay? And this is an example of not isolated system, because there is some beam who in some way can arbitrarily in time modify this acceleration constant explicitly, not by acting on QI, PI like directly, but through this additional term in Hamiltonian. Okay, and when there is, as physicists say, when there is no explicit dependence on time, which is captured by partial derivative of Hamiltonian with respect to time, the total derivative of the Hamiltonian would vanish, which means the energy of the system conserved. If there is explicit dependence of time, then the Hamiltonian will not be conserved, and hence neither the energy. Do you have questions?
Can you tell us a real example of this case?
What?
Give us a real example of this case.
A real example, for instance, we start to, okay, you may hopefully know that electromagnetic radiation is light, right? So if I take a glass of water and I start to switch on very strong ultraviolet lamp, okay, it will create, I will switch it on, off, it will create magnetic oscillations inside, I mean, electromagnetic wave, which is oscillations of electromagnetic field. And it will change.
Okay.
And actually, you know that if you use strong light, you start to heat system. That's because the system starts to absorb energy of the light, and it is captured through time dependence of Hamiltonian.
Yeah.
Other questions? Okay. No other questions. Let's. Okay, so that's a bit late. Probably you had a long day already by this time. All right. So that was today. I was trying to show you how Hamiltonian, which we used last time to define the microcanonical ensemble, can give us interpretation of internal energy of a system, how it is related, how its time dependence related to the question of a system being isolated. So if we see that system is isolated, there is no explicit time dependence of Hamiltonian terms, energy is conserved. When there is some external agent that can put energy or extract energy from the system, there appears time-dependent term in Hamiltonian, like, for example, with the ultraviolet line. And so we will continue next time with the internal energy and the first law of thermodynamics. Okay.